Alright guys, so this is our first Flip the Classroom lesson of Chapter 3, and it's also going to be our first lesson of Chapter 3, Exponential Functions. So before we talk about exponential functions, I want to talk about exponents a little bit and exponential properties. So in general, let's start out with what an exponent is. So an exponent is a number that counts how many times we multiply a number by itself, right? And that's the only thing it counts. So right here, if I've got 3 squared, right, 2 being the exponent, I'm multiplying 3 by itself 2 times, right? So that's 3 times 3, or 9, right? If I have 3 to the 3rd power, right, now I'm multiplying 3 by itself 3 times, right? So we could say that's 3 times 3 is 9, times 3 again would be 27, right? If we've got 3 to the 1 power, basically that means we're multiplying 1 3, and we would just get 3, right? All of these guys we want to think of as being multiplied by a silent one. And in fact, we can basically say all numbers are being multiplied by a silent one, since anything times 1 is itself. So right here, if I had 5, just 5, we could say is equivalent to 5 times 1, right? So right here, when I say that I have 3 to the 0 power, right, that means I'm multiplying no 3's, and all I've got left is that silent 1 right there, right? Right here, if we have 3 to the negative 1, right, what we want to think is that here we are unmultiplying 1 3, right? So right here, we are multiplying 3 3's, 2 3's, 1 3, 0 3, and when we have a negative 1 exponent, we are unmultiplying 1 3, or dividing by 3. If we've got 3 to the negative 2, we want to think about that as unmultiplying 2 3's, or dividing out 2 3's, multiplying by 2 3's in the denominator, or 3 squared in the denominator, which is going to be dividing by 9, right? So in general right here, we can see that that exponent is really counting how many times we multiply a number by itself, even when it's a negative exponent. When it's a negative exponent, it's basically saying I am unmultiplying 1 3, or unmultiplying however many 3's the power is, right? So negative 2 would be an unmultiplication of 2 3's, or a division of 2 3's, which gives us a division of 9. Okay, so moving on to properties of exponents. If you guys want to sort of fast forward this bit, that's fine. If you feel comfortable with properties of exponents, I'm just going to go through some explanations here, and then we'll get on to talking about exponential functions. So right here, if I've got an exponential expression that's being raised to an exponent, we say that we can multiply the exponents in this case. So why can we do that? Well, let's take a look. If we've got x to the 3 squared, right, x to the 3rd power squared, we can say that that is equivalent to x cubed times x cubed, since we're seeing the square right there, right, multiplying x cubed by itself. And right here, with each of these x cubed, we're multiplying 3x's. So this is 3x's times 3x's. And altogether, how many x's are we multiplying? Well, right here we can count out 6x's, which is the same as x to the 3 times 2, or x to the 6th. If we have 2 numbers that are being raised to an exponent, or essentially 2 bases, we say that we can distribute the exponent through the multiplication. So right here, if I've got something that looks like x y to the 3rd power, right, essentially I can say this is xy times itself 3 times. So right here, xy times xy times xy, right? The relationship between x and y is multiplication, and since multiplication is transitive, we can rearrange this to a multiplication of 3x's, right, or x cubed, and a multiplication of 3y's, or y cubed. So right here, that would basically be the distribution of the cube to both things that we're multiplying, x cubed and y cubed. Keep in mind, and I know I don't have to say this to you guys, but right here, we know that x plus y cubed is not x cubed plus y cubed, right? We cannot distribute an exponent through addition or subtraction. Just want to point that out. So right here, similarly, we can say that if we have a fraction raised to an exponent, we can distribute that exponent to the numerator and denominator. So as an example, let's take a look at x over y cubed, right? So basically right here, this would be x over y times x over y times x over y. When we multiply fractions, we multiply across in the numerators and the denominators, right? So right here we can say we're multiplying 3 x's in the numerator, or x cubed in the numerator, and 3 y's in the denominator, or y cubed in the denominator. And there is our distribution of that exponent of 3 to the numerator and denominator. So this is x cubed over y cubed. If we are multiplying 2 of the same base, we can say that we are adding exponents. I'm going to erase this bit right here. What does this mean? Well, right here, let's say I've got x squared times x cubed. Here we can say we are multiplying 2 x's with our x squared, and then timesing that by a multiplication of 3 x's, right? So altogether, how many x's are we multiplying? 5 x's, right? And right here we can see this as x squared plus, x to the 2 plus 3 in the exponent, or x to the 5th, right? Now right here, we've already talked about this. Basically what we want to think is a negative exponent is basically telling us that we are unmultiplying that base however many times we're seeing that exponent, right? And basically right here we can think of a negative exponent in the numerator being a positive exponent in the denominator. So right here we've got, let's say, x to the negative 2 being 1 over x squared, right? Or a division of 2 x's. Similarly right here we want to take note that if we have x to the negative 2 in the denominator, 1 over x to the negative 2, then that's going to be undividing 2 x's or multiplying by 2 x's. So we're sort of seeing that property happen for both a negative exponent in the numerator and a negative exponent in the denominator. If we have 2 of the same base, right, being raised to different powers, we can see that as a subtraction of the exponents. And how is that? Well, right here, if I've got x cubed over, let's say, x squared, right, I could take that x squared out of the denominator and bring it up to the numerator. But if I did that, I would need to be multiplying by x to the negative 2, right? Since it's a positive exponent in the denominator, it's going to become a negative exponent in the numerator. And now right here, using this property of exponents, we can add those exponents and get 3 plus a negative 2, which would just be x. Now, I tend to think that it's easier to sort of think about this as multiplication and division. So right here, I'm multiplying 3 x's in the numerator. I'm going to divide out 2 of those x's. So 2 of the x's that I'm multiplying in the numerator are canceling with 2 x's that I am multiplying in the denominator or dividing by, and that'll give me just x, right? An x to the 1 power that I'm multiplying in the numerator. Anything we raise to the 0 power is 1, right? So basically right here what we're saying is we're multiplying no a's, and that leaves us with the multiplication of the silent 1. So of course x to the 0 gives us 1, right? When we have a radical, right, we can say that that is equivalent to a 1 over that radical power. So right here, if we have the cube root of x, we could say that that would be equivalent to x to the 1/3, right? Now, basically what we're saying right here is that the cube root, right, and the power of 1/3 have the same property, and that is that they both cancel out the cube. So right here we say that the cube root cancels out with a cube, and if we have x cubed to the 1/3 power, we can use our first property of exponents, right, to say that we would multiply those exponents, which would give us x to the 3 over 3, and that turns into x to the 1, right? So basically right here we can say that a fraction exponent with that root in the denominator and 1 in the numerator is equivalent to a radical of that number, right? Right here we can sort of draw this out a little bit and say that anytime we've got the nth root of a to the m, we can always write that as an exponent of the power over the radical, right? So right here, if I've got x cubed, if I'm taking the square root of that, I could call this x cubed to the 1/2 power, or x to the 3/2 power. Okay, so properties of exponents right there. Let's move on to exponential functions. And we say an exponential function is a function of the form f of x equals a times b to the x, where b is being raised to the x power. In general, we want to think of exponential functions as functions whose inputs are exponents, right? So x is the input for our functions, right? We input x values on the x-axis, and those x values are going directly into the exponent here. We say that a is the initial value, right? And we say that b is the base or the growth factor, right? In general, with our exponential functions, we say b cannot equal 1 or be less than or equal to 0. So we're talking about bases between 0 and 1 or from 1 on to positive infinity, right? If our base is greater than 1, we say we have exponential growth, and we're going to see what that means right here. Going back to the initial value, right, we can sort of see why we call a the initial value when we plug in a value of 0. So right here, if the exponent of 0, right, if I am applying that to my f of x, right, which is 2 times 3 to the x, then I would have 2 times 3 to the 0, right? How many 3's am I multiplying? 0 3's. So right here, that would just give me 2. Right? And in general, right here, you can sort of think of the initial value as basically being the value we get before we've multiplied any 3's. So right here, this gives us the ordered pair 0, 2, which is going to go right there on our xy axis. If we go on, what we can see is our function right here is really tripling the output every time. So we're just multiplying by a 3 for every integer exponent that we plug into our exponential function. So right here we've got 2, and then right here we're multiplying 1, 3, right? So if the exponent is 1, we've got 2 times just 3, which would be 6. So we've got 2 and then 6. We tripled the output there. So right here we would go up 6 now and get that ordered pair. And right here, as we plug in an exponent of 2, right? So 2 is the exponent. Now we've got 3 squared, or 9 times 2 is 18, and we would get the ordered pair 2, 18, and that's not even an ordered pair we can graph on our function. So right here, what we're basically seeing is as we plug in greater exponents, right, going out, we would get larger and larger function values, and that's why we would call this exponential growth. What happens when we plug in negative exponents? Well, right here, if we've got 2 and then 3 to the negative 1, we know that if we raise 3 to the negative 1, that actually means we're dividing by 3 or unmultiplying 3. So this would be 2/3, right? So we're all the way down here to 2/3 with that input of negative 1. That's negative 1 2/3. If we have an input of negative 2, that's 2 and then 3 to the negative 2, which would basically be 2 over a division of 2 3's, right? Or right here, 2 over 9, right? So basically, that exponent of negative 2 becomes positive in the denominator. And again, right here, we are unmultiplying 2 3's or dividing by 2 3's or dividing by 9, right? And so right here, we can call that 2/3. And basically, what we can say here is as this exponent becomes more and more negative, right, we're just going to keep on bringing 3 into the denominator and raising it to higher and higher powers, right? So basically, we're going to get a denominator that's larger and larger. And in general, what we can say here is that we're going to get smaller and smaller numbers as x goes out to negative infinity with those exponents. Now, there's no power we can raise 3 to in order to get a 0 output here. So really what we have is a horizontal asymptote of y equals 0 for our exponential function. We say that if the base is between 0 and 1, it is exponential decay. And right here, plugging in exponents, we can see that right here, of course, when we plug in the exponent of 0, that means we're multiplying no 1/2, right? We're just getting 3. So right here we've got the initial value, which is 0, 3, given to us right there. Right here, when we multiply 1, when we raise 1/2 to the 1 power, basically we are multiplying by 1/2 once, right? And so that's going to give us 3/2. And right here, as we raise that base of 1/2 to higher and higher powers, basically we're cutting in half for every integer exponent that we have. So right here, 1, we get 3/2, right? So right here, we get 3/2, which is approximately right there. And right here, when we raise our 1/2 to the second power, right, with an input of 2, basically we are multiplying by 2 by 1/2 twice, right? So we're cutting that previous value in half, and we're saying that we are getting 3/4. So right here, this is 2 3/4, right? And what we're basically seeing here is that as we raise that base of 1/2 to higher and higher powers, we're cutting our output in half each time, and we are getting outputs that get closer and closer to 0, right? And we're seeing that horizontal asymptote now as we go out to positive. Horizontal asymptote of 0 there. Now right here, as we raise that 1/2 to a negative power, what we can see here is that we're basically going to be multiplying by the reciprocal, right? If we raise 1/2 to the negative power, to the negative 1 power, we are unmultiplying by 1/2, right? Or multiplying by 2. So right here, we're going to get 6 as an output, and we'd get -1, 6 as an ordered pair. So go out to -1 and then go up to 6. And right here, if we raise that 1/2 to the -2 power, right? Then right here, we are unmultiplying 1/2 twice, or multiplying by 2 twice, which would give us a multiplication of 4, and 3 times 4 would give us 12. So right here, immediately we are growing as x goes out to -infinity, right? Right here, we can see why this is exponential decay, right? As we increase our exponent, we get smaller and smaller outputs, right? And we can see why this is exponential growth. As we increase our exponent, we get larger and larger outputs. So right here, what we want to think is that the base greater than 1 gives us exponential growth, and a base in between 0 and 1 gives us exponential decay. And in both cases, we're seeing a horizontal asymptote in one direction. So exponential growth, we've got that horizontal asymptote going out to -infinity. Exponential decay, we've got that horizontal asymptote going out to +infinity. Okay, so let's analyze a graph of an exponential function. So right here, in general, we can sort of plot this guy. This is the doubling function, right? We would say that our a value in this case would be 1, right? So we can sort of plot our initial value as 0, 1. Right here, if we have an exponent of 1, we have 1 multiplication of 2. For an exponent of 2, we'd have 4, 2 multiplication of 2s. For 3, we would have 8. And right here, as we go in the opposite direction, we're unmultiplying by 2 or dividing by 2. So we get 1/2, 1/4, 1/8. And we'd see that horizontal asymptote. Now right here, we can say the domain of this guy is going to be -infinity to +infinity, because we're plugging every single x value into the exponent, right? The range of this guy, we're seeing our function bounded below by that horizontal asymptote of 0, right? So right here we can say, with a horizontal asymptote of y equals 0, we are going from 0 up to +infinity with the y values of our ordered pairs. This function is definitely increasing. We can say on domain, right? Decreasing is not decreasing. It is bounded below, right? With the extrema, we don't have any peaks or valleys, so we can say none. The asymptotes, we have a horizontal asymptote of y equals 0 and no vertical asymptote. Right here, the end behavior, if we write it in with limits, we can say the limit of f of x as x goes out to -infinity is going to be 0, right, for our exponential growth function. And the limit of f of x as x goes out to +infinity is going to be +infinity for exponential growth. Right here, we've got some transformations to look at, so we can, of course, quickly plot our graph. There's our exponential growth function, right? 2 to the x. Right here, if we are thinking about transformations, we want to think about them as this in the same way that we thought about them before. So why don't you guys go through and try these transformations real quick. Okay, so right here, with this first function, we can say that we are subtracting 1 in the exponent, right? So that's going to move our initial value 1 in the positive direction, right? And then we are adding 3. So basically, we're seeing this function have all its y values moved up 3, and that means that the horizontal asymptote is moved up 3. And right here, what we can see is a function that is moved forward 1 unit, right, or to the right 1 unit, and up 3. And it's going to look something like this, right? Right here, we can see that we've got 2 to the negative x, and what we would say is that this is a negative inside the function, or in the exponent, and right here, that's going to mean a horizontal flip, and so basically what we're going to see is our function flipped horizontally across the y-axis, and that makes it an exponential decay function. We can talk about why that is a little bit as well. So right here, in general, what we could say is that this would be, this is equivalent to 2 to the negative 1 to the x, right? We sort of unmultiply that negative 1 in x, and right here we know that 2 to the negative 1 is going to be 1/2, or a division of 1, right? Right here, with this multiplication of negative 3 is going to be 2 things. It's going to be a vertical stretch, right? So we're going from an initial value of 1 to an initial value of 3, and all of the y values are going to be stretched up 3. They're all going to be multiplied by 3. But we're also seeing that negative, which is going to mean a flip over the x-axis, or a vertical flip. So right here, we're seeing our exponential function look something like this. Still with a horizontal asymptote of 0, but now flipped over the x-axis. Okay, so looking on, we can talk a little bit how we want to graph these guys. In general, what I would say is we should really use 3 points to graph any exponential growth or decay function. And this is more or less just to get an idea of the trajectory, right? So what I like to do is plug in an exponent of -1, 0, and +1. Why don't you guys go ahead and give this a shot yourselves, and then we'll talk about what these transformations are going to mean down here. All right, so right here, we raise that 1/2 to the -1 power. And that's going to mean unmultiplying 1/2, or multiplication of 2, which gives us 6. So right here we've got 3/6. Not 3/6, but -1/6. -1/6. So we can plot that guy right there, right? With 0, an input of 0, we know we're multiplying no 1/2, so that's going to be an output of 3. And that gives us our initial value. And with 1, we're multiplying 1/1/2, so basically we get 3/2, which is 3/2, and that guy is going to be right there. And we can see the trajectory of our exponential decay, right, around the x-axis. And of course, we would have that horizontal asymptote as well. All right, so right here, we've tried a little bit of transformations. If you guys want to stop the video real quick right here and try to graph this one and give the analysis of this graph, you can go ahead and do that now. Okay, so right here, first off, we want to say that basically we're taking the graph that we just graphed up there, and we are seeing a negative inside the function, which is going to flip us horizontally. So instead of exponential decay now, we're going to see exponential growth, right? So basically we can say that all of the ordered pairs are flipped over the y-axis, so we're going to get our 3/2 right there and our 6 right here. And after that, what we're seeing is our function moved up 2, which means that horizontal asymptote is going to go from 0 to up 2. So right here, we've got our exponential function. We can talk about the analysis of this guy. We're still plugging every single x value on the x-axis into that exponent. So right here we can say we're going from -infinity to +infinity. The range of this guy has now been moved up 2, right? Since all the y values are moved up 2, now we're still bounded below by that horizontal asymptote, but now it's happening at y equals 2. So we can say that our function is going from 2 to +infinity. It is increasing on its domain. So again, we could say increasing from -infinity to +infinity around its domain. Bounded below, right, by that horizontal asymptote. No extrema. We have the horizontal asymptote of y equals 2, and the end behavior is going to be a little bit different here. As x goes out to negative infinity, right, we now have that horizontal asymptote at 2, right, so we move that horizontal asymptote up 2, and right here we can say as x goes out to positive infinity, we're still seeing our function values go to positive infinity. All right, so right here we can talk a little bit about how we can discern an exponential function by looking at a table of ordered pairs. So right here we're saying find the exponential function from its table. So we're immediately saying that we've got an exponential function right here that is a times b to the x, right? Well, if this is an exponential function, we already have one value, right? We know when our x value is 0 that the y value is going to be our initial value. So here we can immediately say that the a value is 4, right? From there, we have y equals 4 times b to the x. So we still don't know what that b value is, but we've got a list of ordered pairs that satisfy this exponential function, whatever it is. The easiest ordered pair to choose from here is going to be 112, right? And that's because when we raise b to the 1 power, we just get b. And so we're going to have 12 equals 4 times b to the 1, which is just b. And now right here, we can just divide by 4 to get that b value. So we divide both sides by 4, and we get b equals 3, right? So why don't you guys go ahead and try this function right here. We'd say, actually, we want to write the final result here. We would say that this is a table for the exponential function that is y equals 4 times 3 to the x, right? One thing we can also take note of here is that we are growing by 3, right, with each ordered pair that we hit. So right here, basically right here, we've got 4/9. Then if I multiply that by 3, I get 4/3. Multiply that by 3, I get 4. Then I've got 3 times 4, which is 12. Then I've got 36, which is 3 times my 12. So I can see that growth factor in the progression of ordered pairs here, right, as I go down. So why don't you guys go ahead and try this one, and then we'll look at it together. Okay, so right here, immediately we can say a equals 8, right? And then from there, we can say that we have y equals 8 and then b to the x. We can take the next ordered pair we have, or basically the ordered pair with an exponent of 1. And right here we can say that we have 2 equals 8 times b to the 1. B to the 1 is just b, so when I divide by 8 on both sides, I get b equals 1/4. And right here, this is the exponential function, y equals, and then 8 times 1/4 x, right? And again, right here, we can see those ordered pairs being decreased by 1/4 as we go from integer exponent to integer exponent, right? Okay, so exponential function base e. So e is a number a lot like pi that is basically an irrational number. It kind of looks like it's repeating here, but in general what we'd say is it's not repeating. There's no way for us to represent it as a fraction. And what we want to think of it as, we just want to think about it as another base, right? So basically, the exponential function base e is going to be, it's going to look the same as any other exponential functions. It does have some special properties that we'll hit on later, but in general right here, what we can say is that it's going to look like any other exponential function. Right here, we can say that we have an initial value of 1, so we can sort of plot that ordered pair. Then right here, when we raise e to the 1 power, we get e, or approximately that 2.7182 whatever, right? So right here, we get that value. And then if I raised e to the negative 1, I would get 1 over e as the output. And basically, that would be the reciprocal of this guy, which is basically a little bit greater than 1/3, right? So right here, graphing this, we would see a function that looks something like this. And if we analyzed it, we would basically see that exact same analyzation of the exponential growth function. Why don't you guys go ahead and analyze this real quick yourselves, and we can go ahead and talk about the logistics function from here. Okay, so right here, we can go ahead and analyze this function, and we will get a domain of negative infinity to positive infinity. we can say the range is going to be from that horizontal asymptote of 0 up to positive infinity. We're increasing on domain, right? And right here we are bounded below. And right here we have no extrema. We've got the horizontal asymptote of y equals 0, and the end behavior is the same end behavior we'd see for any exponential growth function. That isn't manipulated, hasn't been moved up or down. Right here as x goes out to negative infinity, we're hitting that horizontal asymptote of 0. And right here as x goes out to positive infinity, we're going up to positive infinity because e is a number greater than 1, so we just keep on multiplying by that number greater than 1, and we're going to get larger and larger values. Okay, so I want to take a break right here before we jump into the logistics function. So I'm going to pause this, and we're going to break this up into 2 videos, and we will look at the logistics function in the next video.